There is something in the night sky that does not belong, not a comet drifting on its long elliptical path back toward the sun, not a black hole pulling light into its silence, not some exotic form of matter our instruments have yet to properly catalog. What does not belong is something far more fundamental, something so basic to our understanding of physics that its existence quietly dismantles one of the most confident assumptions science has ever made. And if what you are about to hear unsettles you, if it leaves you feeling like the ground beneath your understanding of reality has shifted slightly, then stay with this, because this is one of those rare ideas that, once properly understood, you cannot unfeel. If this kind of thinking reaches you, consider subscribing. There are people looking for exactly this, and they deserve to find it. Now, back to the thing that does not belong. It is light, ordinary light, the same light that warms your skin on a winter morning, the same light your eyes are using to read these words, the same phenomenon that has underpinned virtually every significant discovery in the history of astronomy, because for most of human history, light was the only messenger the universe sent us, and we learned to read it with extraordinary precision. We mapped galaxies with it. We measured the age of the cosmos with it. We traced the architecture of the observable universe across billions of light years, using nothing more than the patient accumulation of photons striking carefully constructed instruments on mountaintops and in the cold silence of orbit. We assumed we understood light. We assumed it was one of the few things in this universe that was genuinely, reliably simple. We were wrong, and the evidence for exactly how wrong we were is sitting in the plain sight, in data that has been published, peer-reviewed, and accepted by the mainstream scientific community. This is not a fringe claim. This is not speculation. This is what the numbers actually say when you refuse to look away from them. Here is what the science has confirmed. When we measure the oldest light in the observable universe, the cosmic microwave background radiation, the thermal afterglow of the Big Bang itself, first mapped in breathtaking detail by the WMAP satellite, and then refined to an almost surreal level of precision by the European Space Agency's Planck mission between 2009 and 2013, we detect photons, real, measurable, undeniable photons, light that has been traveling through the fabric of space for approximately 13.8 billion years, arriving at our instruments after a journey so long it predates the existence of every star currently burning in every galaxy we have ever observed. These photons are the oldest light we have ever measured. They are, by every standard definition, a direct image of the universe in its infancy. And yet those photons were born into a universe that had no business producing them in any form we could ever receive. To understand why, you need to understand what the early universe actually was, not what it looked like, because it looked like nothing, in the most literal sense possible. What it was, in the first 380,000 years after the Big Bang, the universe was not the cool, transparent, largely empty expanse it is today. It was a plasma, a dense, violent, electrically charged fog of protons and electrons, so extraordinarily hot, millions of degrees throughout, and so extraordinarily compressed that light could not move freely within it. Every photon that attempted to travel any meaningful distance was immediately absorbed by a charged particle and re-emitted in a random direction. The universe was, in the most precise, physical sense of the word, opaque. There were no clear corridors. There were no open pathways. There was no sky to cross. There was only a blinding, impenetrable wall of energy in every direction, and any photon born into that environment was trapped. endlessly, scattering, endlessly redirected, going nowhere. Which means the light we see today, the oldest light we have ever measured, could not have escaped during that era. And yet, here it is. Something happened approximately 380,000 years after the Big Bang. Something that cosmologists call the epoch of recombination, a name that is technically accurate but almost comically understated given what it actually describes. As the universe expanded, it cooled. The temperature dropped to roughly 3,000 Kelvin, still extraordinarily hot by any human standard, but cool enough for a process of breathtaking consequence to begin. The free electrons that had been keeping the universe opaque started combining with protons to form neutral hydrogen atoms. Not ionized hydrogen, neutral hydrogen, stable atoms. Atoms that did not continuously intercept and absorb photons in the same violent way the plasma had. And as those neutral atoms formed, the universe became transparent. Not gradually, over billions of years. Relatively swiftly, in cosmic terms, almost instantaneously, the fog cleared. The wall of plasma that had imprisoned every photon in an endless, scattering prison simply dissolved. And the light that had been trapped inside that fog, the light that had been building pressure like steam inside a sealed vessel for 380,000 years, was suddenly free. It streamed outward in every direction, across the entire universe, all at once, an unimaginably vast pulse of radiation, released simultaneously from every point in space, expanding in all directions, cooling as it traveled, stretching as the universe continued to expand around it, until 13.8 billion years later, it arrived here, at Earth, at our instruments, at the Planck satellite's detectors, as a faint, cold microwave glow, barely above absolute zero. That glow is the cosmic microwave background. That is what we are measuring. And for a long time, astronomers assumed that once they understood the mechanism of its release, recombination, neutral hydrogen, the clearing of the plasma, they understood the light itself. But the more carefully they measured it, the more clearly they saw that the light was carrying a message no one had expected to receive. The message was written in temperature. The cosmic microwave background is not perfectly uniform. If it were, if every photon from every direction in the sky arrived at exactly the same temperature, that would actually be the simpler story. But the CMB has subtle variations, fluctuations, tiny differences in temperature from one patch of sky to another, at the level of roughly 1 part in 100,000. These fluctuations are real. They have been mapped in extraordinary detail, and they are the seeds of everything. The slight overdensities in the early universe that gravity eventually amplified into galaxies, galaxy clusters, filaments, the entire cosmic web of large-scale structure we observe today. Those fluctuations are fascinating, but they are not the message. The message is in the uniformity that surrounds the fluctuations, in the fact that despite those tiny variations, the overall temperature of the cosmic microwave background is the same, to a precision of better than 1 part in 100,000, across the entire observable sky, every direction, every patch, every region of the universe, no matter how far apart. The same temperature, the same history, the same fingerprint. And here is why that should stop you completely. The observable universe is approximately 93 billion light-years across. Not because it is 93 billion years old, it is only 13.8 billion years old, but because the expansion of space has carried distant regions far beyond where their light would have reached had space been static. The regions of the universe We observe in opposite directions of the sky, the microwave background coming from the north and the microwave background coming from the south, so to speak, are separated by distances far greater than light could have crossed in the entire history of the universe. Under the known, established standard laws of physics, those regions have never been in contact with each other. Information has never passed between them. They have never been close enough for any process of any kind to bring them to the same temperature, and yet they are at the same temperature. Not approximately, not almost, the same. This is not a coincidence. Coincidences at this scale do not exist in physics. The universe is not in the habit of producing perfect accidents across 93 billion light years. What this uniformity is telling us, what the data has been saying with quiet insistence for decades, is that those regions were once connected. They were once close enough, once in sufficient causal contact that they reached thermal equilibrium. They shared the same heat, the same conditions, the same physics, and then something separated them. Something pushed them apart at a speed that defies intuition and challenges the very framework we use to understand causality. The problem has a name. Physicists call it the horizon problem. It was recognized and articulated clearly in the 1960s and 1970s, and it sits at the heart of why the oldest light in the universe is, in a precise and verifiable sense, older than the universe as the standard Big Bang model describes it. Because if those regions were never in contact, and under a simple Big Bang model they never were, then the uniformity of the cosmic microwave background is not just mysterious. It is impossible. It is a measurement that the model we use to describe the universe explicitly predicts should not exist, and yet the measurement exists. The data exists. The light exists. Something is wrong with the standard picture, or more precisely, the standard picture is incomplete. There is a chapter of cosmic history that precedes the Big Bang as we classically understand it, a chapter so violent, so extreme, so geometrically bizarre that it rewrites the opening of the universe's story entirely. That chapter does not begin with the familiar image of a point expanding outward. It begins with something stranger, something that, once you understand what it implies, makes the universe feel simultaneously larger and more claustrophobic than you have ever imagined. Before we go there, sit with the light for a moment longer. Those photons are real. They are arriving at Earth right now from every direction, carrying the faint thermal memory of a moment 13.8 billion years ago, when the universe first became visible. If you could see in microwaves, if your eyes were sensitive to that frequency, the entire sky would glow. Not bright, not hot, but present. Everywhere. A pale, luminous shell surrounding everything you have ever seen or ever could see. You are inside the oldest light in the universe. Right now, it is passing through you, through every atom in your body, every atom in the planet, every atom in the solar system. It has been doing so since long before there was an Earth to pass through, and it is telling you something about the very first instant of existence, something that contradicts the intuitive story of a beginning, something that forces cosmologists to add a chapter before chapter 1, something that the light itself, by its mere existence, its mere uniformity, its mere perfection, insists upon. The universe, before it became the universe you know, was somewhere else, entirely. It was smaller than anything you have ever been asked to imagine, and it was moving in a way that even now, with all the mathematical tools at our disposal, strains the boundaries of physical intuition. Because the expansion of the universe, the expansion we measure today, through the redshift of distant galaxies, through the recession of the cosmic horizon, through the accelerating separation of all things from all other things, is not the whole story. It is not even the beginning of the story. Before the expansion, there was an explosion of space itself, not an explosion in space, an explosion of space, a period during which the fabric of the universe stretched at a rate so far beyond the speed of light that the entire observable cosmos, every galaxy, every cluster, every supercluster, every filament of the cosmic web, originated from a region smaller than a single proton, one proton, smaller than one proton. Everything you have ever known, every star, every planet, every atom, compressed into a space so unimaginably small that our language does not have adequate tools to describe it without resorting to the notation of mathematics. And then it expanded, not slowly, not gently, instantaneously, in any meaningful sense of the word. It became enormous. The light carries the proof of this. The uniformity of the cosmic microwave background is not a problem to be explained away. It is evidence. It is a measurement of a process that happened before the universe was old enough to be described in any framework we currently possess. The light is older than the standard model of cosmology. It is a relic of physics that the standard model cannot fully contain. This is where cosmology stands today, not at the edge of solved problems, but at the edge of a much larger mystery than the one it started with. The more precisely we measure the ancient light, the more clearly we can read what it is telling us about the conditions of the very early universe. And the more clearly we can see that those conditions demand an explanation that goes further back than the Big Bang, further back than time as we ordinarily experience it, further back than any event we can directly observe. The light has survived for 13.8 billion years to tell us something. And what it is telling us is not the story of a beginning. It is the story of a transition, a boundary between one phase of existence and another, a moment when something inconceivably strange and powerful stopped, and something we call the universe began. What was that something? What drove it? What governed it? And most unsettlingly of all, is there any reason to believe it happened only once? These are not rhetorical questions. They are the active, unresolved, fiercely debated frontiers of modern cosmology, and the answers, the partial answers we have assembled so far, and the deeper questions those answers expose, will do something to your understanding of reality that cannot be undone, because the further you follow the light, the older it gets, and the older it gets, the less certain the universe becomes. That expansion of uncertainty, of scale, of strangeness, is exactly where we are going next. There is a particular kind of intellectual courage that separates the scientists who advance human understanding from those who merely catalog it. It is not the courage to work harder or longer or with more sophisticated instruments. It is the courage to look at a model that explains nearly everything, a model that has been tested, validated, and celebrated, and say, quietly but without hesitation, that it is not enough, that behind its successes lies a silence that sounds like an answer but is actually a question nobody has yet been willing to ask out loud. In the winter of 1979, a young physicist named Alan Guth was doing exactly that. He was sitting at a desk at Cornell University, largely unknown outside a narrow circle of theoretical physicists working through the mathematics of the early universe, with the methodical patience of someone who does not yet know they are about to change everything. His notebooks were filling with calculations. His calculations kept arriving at the same destination, and that destination was not a solution. It was a diagnosis. The universe, as described by the best cosmological model of the time, was broken. Not in the way that a theory is broken when it makes a wrong prediction. Wrong predictions can be corrected, parameters adjusted, equations refined. It was broken in the way that a foundation is broken when you discover it was never actually resting on anything solid. The standard Big Bang model, for all its extraordinary power, contained within it a set of problems so fundamental that no amount of adjustment could resolve them. They could only be resolved by going back further, by adding something before the beginning. Guth called his notes on the subject, with characteristic understatement, spectacular realization. What he had realized was this: the only way to explain the universe we actually observe, the uniform, flat, carefully structured cosmos that the cosmic microwave background reveals, was to propose that in the first unimaginably brief moments of its existence, the universe had undergone a period of expansion so extreme it bore no resemblance to anything in ordinary physical experience. He called it inflation. And once you understand what that word actually means, not as a metaphor, not as a shorthand, but as a precise description of what the mathematics demands, the universe becomes a stranger place than you were prepared for. Let's be precise about the problem Guth was solving, because the precision matters enormously. You already know about the horizon problem, the fact that opposite regions of the cosmic microwave background share the same temperature, despite never having been in causal contact under the standard Big Bang model. But Guth was not only confronting that, he was confronting two additional problems, each of which pointed in the same direction, each of which demanded the same extraordinary solution. The second problem is called the flatness problem. It concerns the geometry of space itself. General relativity, Einstein's description of gravity as the curvature of spacetime, tells us that the universe can have one of three possible geometries. It can be positively curved, like the surface of a sphere, in which case the total energy density of the universe exceeds a critical value and space curves back on itself. It can be negatively curved, like the surface of a saddle, in which case the universe is open and geometry diverges from the flat Euclidean rules you learned in school. Or it can be precisely flat, balanced exactly at the critical density, with parallel lines remaining parallel forever, with the angles of a triangle summing to exactly 180 degrees across any scale. Measurements of the universe, including the extraordinarily detailed Planck mission data, tell us that the universe is flat, not approximately flat, not almost flat, flat to a precision of better than 0.5%, which is itself almost certainly limited by our instruments rather than by any genuine departure from perfect flatness. Now here is why this is a problem. In the standard Big Bang model, the flatness of the universe is extraordinarily sensitive to initial conditions. If the energy density of the very early universe deviated from the critical value by even 1 part in 1060, a number so close to zero it makes zero look extravagant, the universe would have either collapsed back on itself in a big crunch within seconds, or expanded so rapidly that matter could never have clumped together to form anything at all. No galaxies, no stars, no atoms, nothing. The universe we observe requires that the initial conditions were fine-tuned to a precision that, in the standard Big Bang model, has no explanation. It simply is what it is. The universe happened to start flat, and here we are. Guth recognized that this was not an explanation. It was a placeholder, and inflation dissolved it completely because a period of accelerated expansion in the early universe would naturally drive space toward flatness in the same way that the surface of a balloon becomes locally indistinguishable from a flat plane as you inflate it. The larger the balloon, the flatter any small patch of its surface appears. Inflation made the universe so large so quickly that the observable portion, everything we can see in any direction, is an infinitesimally small patch of a much larger whole, and any initial curvature was stretched away to nothing. The flatness of the universe is not a coincidence. It is a consequence of inflation, and inflation, in turn, was not invented to explain flatness. It was invented to explain the horizon problem. The fact that it simultaneously resolves the flatness problem with no additional assumptions is the kind of convergence that physicists recognize as a sign they are close to something real. But now, we need to sit with what inflation actually is, what it physically means, because this is where the mathematics starts doing something to your intuition that takes a moment to fully absorb. Inflation is not the expansion of the universe in the ordinary sense. The expansion we measure today, the recession of distant galaxies, the redshifting of light, the gradual increase in the distance between all things, is a gentle, continuous process driven by the initial energy of the Big Bang and more recently, accelerated by dark energy. It is fast by human standards, but modest by cosmic ones. It is expansion as we know it. Inflation was something categorically different. In a period lasting somewhere between 10 to 36 and 10 to 32 seconds after the Big Bang, a duration so brief it has no analogy in any physical process you have ever encountered. The universe expanded by a factor of at least 10 to 26. Some models suggest the expansion factor was far, far larger. What had been a region smaller than a proton became, in that single instant of cosmic violence, a volume larger than the observable universe is today. And critically, this is the point that Einstein's relativity permits, but that human intuition resists. This expansion did not violate the speed of light. Einstein's equations prohibit matter and information from moving through space faster than light. They say nothing about the expansion of space itself. Space is not matter. Space is not energy. Space is the stage on which matter and energy perform, and the stage can grow at any rate whatsoever without violating any physical law. During inflation, space itself expanded faster than light, not the things in it. The things in it were essentially stationary relative to their local surroundings. The distance between them grew because the metric of space, the mathematical description of how distances are measured, was stretching at a rate that dwarfs the speed of light by a factor so enormous it is difficult to write as a number without losing the sense of what it means. Every photon born during the inflationary epoch was carried outward on the expansion of space, like a cork on the surface of a wave that is moving faster than the cork can swim. Not just faster, incomparably, unfathomably faster. And this is why the light is older than the universe, in any intuitive sense. The photons that would eventually form the cosmic microwave background were born into a space that was running from them at speeds they could never match. They chased a receding horizon. They were, for a time, cosmological prisoners, present in a universe they could not see the edges of, embedded in an expansion they could not escape, stretched and cooled and carried outward across distances that grew by the second. For 380,000 years, they scattered. And then, as we saw in Chapter 1, the plasma cleared, and they were free. But the universe they were released into was already unimaginably vast, already structured, already carrying in its large-scale architecture the imprint of what inflation had done to it. Now, we need to ask the question that Guth's proposal, for all its explanatory power, could not answer. The question that sits at the center of inflationary cosmology, like a locked room that every passing physicist can see, but none has yet been able to open. What caused inflation? The theoretical scaffolding around this question is well developed and sophisticated. The leading answer proposes a scalar field, a form of energy permeating all of space, with no direction, no charge, no spin, called the inflaton field. In the very early universe, this field is thought to have been displaced from its lowest energy state in much the same way that a ball resting on a hillside is displaced from its lowest energy state at the bottom of a valley. The field held energy, a kind of potential energy embedded in the structure of space itself, and that energy acted as a repulsive force, driving the exponential expansion. As the field slowly rolled toward its minimum, as the ball rolled down the hill, inflation continued. When the field reached its minimum, inflation ended, and the energy contained within it was released into the universe as a flood of particles and radiation. That flood is what we call the Big Bang. In this picture, the Big Bang was not the beginning of the universe. It was the end of inflation. It was the moment the inflaton field decayed and filled the cosmos with the hot plasma that would eventually cool into atoms, stars, and galaxies. This is a beautiful framework. It is mathematically consistent. It makes predictions that have been tested and confirmed. The spectrum of fluctuations in the cosmic microwave background, the flatness of the universe, the large-scale homogeneity of cosmic structure, with a precision that commands genuine respect. But the inflaton field itself has never been detected. Its properties are inferred, not measured. The shape of its potential energy landscape, the hill that determines how inflation begins and ends, is not derived from any deeper theory. It is chosen to match the observations. And the question of what the inflaton field actually is, what it is made of, what laws govern its behavior, and where it came from, sits unanswered in the foundations of cosmology, with the same quiet stubbornness it has maintained since Guth first wrote it into the equations. We have a mechanism. We do not have a cause. And here is where inflation becomes not merely a solution to cosmological problems, but a generator of philosophical ones. Because the same mathematics that resolves the horizon problem and the flatness problem contains, embedded within it, an implication that many physicists find either deeply exciting or deeply troubling, depending on their temperament. The implication is this: there is no compelling reason to believe that inflation happened only once. If the inflaton field can decay in one region of space, ending inflation and producing a Big Bang, it can, in principle, decay differently in other regions. In the mathematics of what Andre Linde at Stanford developed into a framework called chaotic inflation and then eternal inflation, the inflaton field does not decay uniformly across all of space simultaneously. It decays in patches. In some regions, inflation ends. In others, it continues. And in those continuing regions, the exponential expansion creates new volumes of space faster than decay can consume them. Inflation, once started, may never stop globally. It may still be happening right now, not in our observable universe, but in the vast regions beyond our cosmic horizon, in a background of perpetually inflating space from which new universes continuously bud off like bubbles forming in a boiling liquid. Each bubble is a separate universe governed by the particular energy landscape of the inflaton field in that region. Each bubble has its own physical constants, its own particle masses, its own cosmological history. Our universe, with its particular speed of light, its particular gravitational constant, its particular fine structure constant that determines how atoms work, is one bubble, one among a potentially infinite number of others. This is the multiverse, and it is not a fantasy invented by science fiction. It is a mathematical consequence of the same framework that explains why the cosmic microwave background is uniform, why the universe is flat, and why the oldest light in the sky has the properties it does. The same equations that describe the light describe the abyss. Take a moment to feel the full weight of that, the uniformity of the ancient light, that measurement of perfect sameness across regions of the universe that should never have been in contact, leads, through a chain of rigorous physical reasoning, to the conclusion that our universe may be one of infinitely many, each invisible to the others, each causally disconnected, each the product of a random fluctuation in an inflaton field that may have been inflating forever. The light that has been traveling for 13.8 billion years to reach us is carrying, embedded in its temperature map, the imprint of a process that produced not just our universe, but potentially all universes. And we can read that imprint with our instruments. We can measure the fluctuations, map the spectrum, compare the predictions of different inflationary models against the data, but we cannot see beyond our horizon. We cannot confirm or deny the existence of other bubbles. We cannot reach the inflaton field or peer behind the moment of our own Big Bang. The multiverse, if it exists, is permanently beyond the reach of any observation we could ever make from within our bubble. Physics has produced a theory that explains almost everything we can see, and whose logical extension is a cosmos almost none of which we can ever see. That is the position Alan Guth's spectacular realization has led us to, not through careless speculation, but through mathematics that has been tested against the finest measurements in the history of science and confirmed. The universe is far larger than the light can tell us. What lies beyond the horizon is not darkness. It is the rest of the story, a story written in a language we cannot fully read, about a cosmos we cannot fully observe, structured by physics we cannot fully reach. And even within the small slice of it we can see, even within the 93 billion light years of our observable universe, the light is telling us things that the models have not yet caught up with, because the cosmic microwave background is not perfectly uniform, and in the places where it deviates, in the anomalies that the Planck mission found and could not explain, there may be written something even stranger than everything inflation has already shown us, something that points not outward to other universes, but backward, before the Big Bang, before inflation itself, before the beginning of the beginning. Imagine you are standing at the edge of an ocean at night. The water stretches out before you in every direction, dark and vast, and somewhere out there, far beyond where your eyes can reach, the surface continues. You know it continues. You know there are depths and distances out there that exceed anything you can perceive from where you stand. But the boundary of your vision is not the boundary of the ocean. The ocean does not end where your sight does. Now imagine that the ocean is expanding, not the water within it, the ocean itself. The space between you and every point on its surface is growing continuously in all directions. And imagine that beyond a certain distance, the surface is receding from you, faster than light can travel toward you. The waves that originate from those regions will never reach your shore, not because they are too small, not because the ocean absorbs them before they arrive, but because the geometry of the ocean itself, the curvature and expansion of the space that contains it, means that no signal originating beyond that boundary can ever cross it. That boundary exists in the real universe, right now, around you. It is called the cosmic event horizon, and understanding what it means, truly sitting with what it implies about the nature of the universe and our position within it, is one of the more quietly devastating experiences that cosmology has to offer. We have been tracing the oldest light in the universe. We have followed it from the moment of recombination, when the plasma cleared and the photons were freed. We have traced it back through the inflationary epoch, where the same mathematics that explains its uniformity opens the door to a cosmos of unimaginable scale. And now we arrive at a question that the light itself forces upon us, not about where it came from, but about where it is going, about what will happen to the information it carries as the universe continues to expand. Because the expansion of the universe is not a static background condition, it is a dynamic process, and the dynamics have a direction. In 1929, Edwin Hubble published observations confirming what Georges Lemaitre had already derived from Einstein's equations 2 years earlier. The universe is expanding. Galaxies are receding from us in all directions, and the further away they are, the faster they are moving. This was the discovery that made the Big Bang not merely a theoretical curiosity, but a physical necessity. If the universe is expanding today, it was smaller yesterday, smaller still the day before. Follow the expansion backward, far enough, and everything converges to a point, a singularity, a beginning. That much has been part of the cultural vocabulary of cosmology for decades. What is far less discussed? What exists in the technical literature with full mathematical precision but rarely makes its way into the popular understanding of the cosmos is what the expansion means, not for the past, but for the future, and specifically, what it means for the light. In 1998, 2 independent research teams did something that physicists rarely do with any degree of drama. They announced a result that none of them had expected, that contradicted the existing consensus, and that carried implications so far-reaching that the scientific community took years to fully absorb them. The teams, the Supernova Cosmology Project, led by Saul Perlmutter at Berkeley, and the High Z Supernova Search Team, led by Brian Schmidt with key contributions from Adam Rees, were using a particular type of stellar explosion as a measuring tool. Type Ia supernovae occur when a white dwarf star accumulates enough mass to trigger a catastrophic thermonuclear explosion, and they do so with a consistency that makes them extraordinarily useful as standard candles. Because their intrinsic brightness is known, measuring how bright they appear from Earth tells you precisely how far away they are. Map enough of them across enough of cosmic history, and you can reconstruct the expansion rate of the universe across billions of years. What they expected to find was deceleration. The universe was born in the explosion of the Big Bang, and gravity, the mutual attraction of all matter for all other matter, should have been gradually slowing the expansion down ever since. Like a ball thrown into the air, the universe should have been losing speed with every passing billion years. What they found was the opposite. The expansion of the universe is accelerating. The universe is not slowing down, it is speeding up. Galaxies that were already racing away from us are racing away faster than they were a billion years ago. And a billion years from now, they will be racing away faster still. Something is driving the expansion, not resisting it, but actively amplifying it. and that something appears to grow stronger as the universe ages. Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011 for this discovery. The force driving the acceleration was given a name, dark energy, and that name, for all its dramatic resonance, is essentially an admission of ignorance dressed in technical clothing. We do not know what dark energy is. We do not know where it comes from. We do not know whether it is a fixed property of space itself, Einstein's cosmological constant, a energy density intrinsic to the vacuum, or a dynamic field that evolves over time. We know only that it exists, that it constitutes approximately 68% of the total energy content of the universe, and that it is winning. Gravity is losing. The fabric of space is stretching faster and faster, and as it does, the light has less and less time to reach us before its source disappears beyond the horizon. Here is what this means in practice, and why it transforms the way you should think about everything the ancient light is telling us. Because the expansion is accelerating, the cosmic event horizon, the boundary beyond which light can never reach us, is not fixed. It is shrinking, not in the sense that the boundary is moving closer to us in absolute terms, but in the sense that more and more of the observable universe is falling beyond it. Galaxies that we can detect today, that we can map and measure and photograph with our finest telescopes, are being carried away from us at speeds that will eventually exceed the speed of light relative to our position. And when that happens, their light will never reach us again. The photons those galaxies are emitting right now are already beginning to lose the race. Some of them will make it. Some of them, from the galaxies furthest from us, already retreating at the greatest speeds, will not. They will spend billions of years traveling toward us and never arrive, stretched into frequencies too low to detect, swallowed by the expansion of the space they are attempting to cross. Over the next few trillion years, the sky will empty, not metaphorically, literally. The galaxies beyond our local group, the gravitationally bound collection of galaxies that includes the Milky Way and Andromeda and a handful of others, will recede into invisibility one by one. Their light will redshift into wavelengths too low for any conceivable instrument to detect. They will not disappear because they have died. They will disappear because the universe has outrun their ability to communicate with us. And here is the truly vertiginous implication. A civilization arising in 1,000,000,000 years, in a galaxy that has survived the merger of the Milky Way and Andromeda, orbiting a star burning quietly in that far future cosmos, will look out at a night sky and see almost nothing. A small collection of nearby galaxies in their local group, and beyond that, absolute darkness, no cosmic microwave background to detect, stretched now beyond any possible frequency, no distant galaxies to map, no evidence of large-scale structure, no hint that a universe of hundreds of billions of galaxies exists beyond what they can see. They will have no way of knowing what we know now. Sit with that for a moment, because it contains something that goes beyond astronomy. We are living in a cosmologically privileged window. Not privileged in any spiritual or anthropocentric sense. Privileged in the precise sense that the universe is currently at a stage in its evolution where its own history is still visible. The cosmic microwave background still reaches us. The most distant galaxies are still within our observational horizon. The architecture of the cosmos, the filaments and voids and clusters that inflation seeded and gravity sculpted, can still be read. In the deep future, all of that evidence will be gone, erased not by destruction, but by expansion. The universe will have hidden its own origin behind a horizon no telescope can cross. Future cosmologists, if they exist, will inherit a universe that appears to be nothing more than a small island of matter in an infinite void. They will have no empirical basis for concluding that a Big Bang occurred. They will have no way of measuring the expansion rate, because there will be nothing outside their local group against which to measure it. The knowledge we have, right now, the picture of the cosmos that the Planck mission gave us, the supernova data that revealed dark energy, the large-scale galaxy surveys that traced the cosmic web. This knowledge is available to us because we exist at precisely the right moment, a billion years earlier, and the instruments did not exist. A trillion years later, and the evidence will not exist. We arrived just in time to read the light, and the light is already beginning its farewell. But here is where the story turns, in a direction you may not have anticipated, because the horizon is not only a limitation in space, it is a limitation in time, and the two are connected in a way that forces a confrontation with the most disorienting aspect of the observable universe. Everything we see when we look at the sky is the past, not the recent past, the ancient past, stretching back billions of years, depending on the distance of the object. When we observe a galaxy 10 billion light years away, we are seeing it as it was 10 billion years ago, before our sun existed, before the Earth had formed, before the first complex chemistry that would eventually produce life had even begun. That galaxy may look completely different today. It may have merged with another galaxy. It may have changed beyond recognition. It may, in some extreme scenario, no longer exist. We have no way of knowing. The information about its current state has not had time to reach us. This is not a technical limitation to be overcome with better telescopes. It is a fundamental feature of the universe. Light travels at a finite speed. The universe has a finite age. Therefore, there is a maximum distance from which light could ever have reached us since the Big Bang. And everything beyond that distance is, in a precise physical sense, beyond our universe. Not beyond space, beyond our universe, beyond causality, beyond any possible observation or interaction. The observable universe is a sphere centered on us, not because we are special, but because we are here. Any observer, anywhere in the cosmos, inhabits their own observable universe, a sphere of the same radius, centered on their own position, containing a different but equally finite sample of the total cosmos. Those spheres overlap. They share content, but they are not identical, and they are all, each one, surrounded by an incomprehensible volume of space that their light cannot reach, and whose light cannot reach them. The observable universe is not the universe. It is a window that is slowly and inexorably narrowing. Now consider what all of this means for the oldest light, the cosmic microwave background, that ancient thermal glow. The message from the epoch of recombination is the oldest light we can observe. It represents our furthest horizon. The surface of last scattering, as it is called, is the wall beyond which we cannot see. Because before recombination, the universe was opaque, and photons could not travel freely. Everything that happened before that moment, the inflationary epoch, the phase transitions of the early plasma, the first fractions of a second after the Big Bang, is hidden behind it. We have been speaking of this as a limitation, but consider it from the other direction. That wall, that surface of last scattering, is also our most distant source of information. It is, in a genuine sense, the edge of the observable universe, not the edge of space, which may extend infinitely in all directions, but the edge of what we can see, the edge of what the light can tell us. And the light from that edge is cooling. It is redshifting. As the universe expands, the wavelength of the cosmic microwave background stretches further into the microwave and eventually into frequencies too low to detect. The wall is not approaching us, but our ability to read it is finite. The precision with which we can measure its temperature fluctuations, map its polarization patterns, extract from it the signatures of inflationary physics, that precision has a ceiling, and we may already be close to it. The Planck mission may have given us the most detailed picture of the cosmic microwave background we will ever have, not because future telescopes will be less capable, but because the signal itself is fading, slowly, imperceptibly, by human timescales, but fading nonetheless. We are reading a document that is being gradually erased, and what that document is telling us, in its temperature maps, in the subtle polarization patterns that carry the imprint of gravitational waves from the inflationary epoch, in the anomalies that the standard model cannot explain, is that our picture of the universe is still profoundly incomplete. There is a cold spot in the southern hemisphere of the cosmic microwave background, larger than inflation-based models predict, colder by a margin that sits at the edge of statistical significance, not definitively anomalous, but not comfortably explained either. There is an asymmetry in the power spectrum between the northern and southern hemispheres of the CMB sky that has persisted across multiple independent analyses. There is a suppression of fluctuations at the largest angular scales that the standard model predicts should not be there. These anomalies may be statistical artifacts. They may be residual instrumental effects that no calibration process has yet fully removed. They may be the fingerprints of foreground contamination from our own galaxy, dust, synchrotron, radiation, all the messy astrophysical processes that intervene between the CMB and our instruments. Or they may be something else entirely, because there is another possibility, a possibility that a growing number of serious physicists have begun to take seriously enough to publish in peer-reviewed journals, to debate at conferences, to build theoretical frameworks around. A possibility that, if correct, would not merely refine our understanding of the early universe. It would require us to confront the existence of something before the beginning. The anomalies in the ancient light, the cold spot, the hemispherical asymmetry, the power suppression are, in at least some theoretical frameworks, consistent with signatures that would be produced by the universe before our Big Bang. Not a universe that existed in the same space and time, a universe that existed in a different aeon, a different cycle of cosmic history, whose gravitational imprint somehow survived the transition between one era of existence and the next, and left its mark on the oldest light we can see. The light, in other words, may not only be older than the universe in the inflationary sense, older than the plasma, older than the first atoms, older than anything we ordinarily think of as the beginning. It may be carrying, embedded in its coldest regions, in its most subtle asymmetries, in the patterns that the standard model cannot account for, the ghost of something that existed before the Big Bang itself. That is the possibility the data refuses to rule out, and the physicist who has built the most rigorous theoretical framework around it is someone whose credentials make the idea impossible to dismiss. His name is Roger Penrose, and what he has proposed is not a speculation. It is a geometry. There is a question that most scientists learn early in their training to treat with extreme caution, not because it is unscientific, not because it is unanswerable in principle, but because the history of physics is littered with careers that came apart at the seams trying to answer it without sufficient mathematical discipline. The question is deceptively simple, and it sits beneath every cosmological model ever constructed, waiting with the patience of something that has nowhere else to be. What came before? For most of the 20th century, the standard response was to deflect. Before the Big Bang, the question has no meaning. Physicists would say, time itself began at the singularity. There is no before, in the same way there is no land south of the South Pole. The question assumes a temporal framework that did not exist prior to the moment it asks about. And for decades, this response was accepted, not because it was satisfying, but because it was mathematically defensible, and because no one had produced a credible framework for doing better. That changed, not with a sudden announcement, not with a single experiment, but with the slow accumulation of something far more powerful than experimental data, a geometric argument so rigorous, so internally consistent, and so confronting in its implications that it forced the question back onto the table with a weight that deflection could no longer bear. The argument came from Roger Penrose, and to understand what he is proposing, you first need to understand something about the man, because in physics, the source of an idea matters less than the quality of the mathematics, but the source of this particular idea is relevant in ways that go beyond credibility. Roger Penrose is not a fringe theorist. He is one of the most decorated theoretical physicists and mathematicians alive. He shared the 2020 Nobel Prize in Physics, awarded at the age of 89, for proving mathematically that black holes are a direct and inevitable consequence of general relativity. This was not a modest contribution. This was the theorem that transformed black holes from a theoretical curiosity into a physical necessity, that showed Einstein's own equations demanded the existence of singularities under realistic physical conditions. Without Penrose's work in the 1960s, the entire subsequent history of black hole physics, Hawking radiation, the information paradox, gravitational wave astronomy, the first image of a black hole captured by the Event Horizon Telescope, unfolds differently, if at all. This is the man who looked at the cosmic microwave background and concluded that the anomalies it contains are not noise. They are memories. His framework is called conformal cyclic cosmology, and it proposes something that sounds, on first encounter, like mythology dressed in mathematics. It proposes that our Big Bang was not the beginning of time. It was a transition, a boundary between one cosmic aeon and another, and that the universe we inhabit is not the first universe that has ever existed, but one cycle in a sequence of cycles that may extend infinitely in both directions, a cosmos that has no beginning and no end, only an endless succession of expansions, each one giving birth to the next. To understand why this is not mythology, you need to follow the geometry. Begin at the end. Not the end of our universe, as we experience it now. Not the death of stars, not the collision of galaxies, not any process occurring on timescales we can intuitively grasp. The far, far future, the unimaginably distant era when the accelerating expansion driven by dark energy has pushed every galaxy beyond every other galaxy's horizon, when the last stars have exhausted their fuel and faded to cold remnants, when neutron stars have decayed, when the protons themselves, if current theoretical estimates are correct, have dissolved into lighter particles over timescales of 1034 years or more. In this future, a future so distant it makes the current age of the universe look like the first microsecond of a human lifetime. The universe contains almost nothing, a diffuse sea of photons and neutrinos and gravitational waves, growing colder and more dilute as the expansion continues. And the black holes? Because black holes do not decay quickly, the process by which black holes slowly radiate energy, Hawking radiation, the quantum mechanical process that Penrose's former collaborator, Stephen Hawking, described in 1974, is extraordinarily slow for massive black holes. A stellar mass black hole takes roughly 1,067 years to evaporate completely. A supermassive black hole at the center of a galaxy, billions of times the mass of the Sun, takes something on the order of 1,096 years to evaporate. These are numbers so large, they strain the architecture of human cognition. But eventually, given sufficient time, even the largest black holes in the universe will radiate away their mass entirely and dissolve into a final burst of thermal radiation. And then the universe contains nothing but radiation, photons, no massive particles, no structures, no clocks, no rulers. A universe composed entirely of light, expanding forever, growing colder and colder, approaching but never reaching absolute zero. Here is where Penrose's geometry begins to do something extraordinary. In general relativity, there is a mathematical operation called a conformal transformation. It is a rescaling of the metric, the mathematical object that describes the geometry of spacetime, that preserves angles and local shapes but changes distances. In ordinary curved spacetime, distances are physically meaningful. The distance between two events matters. But for massless particles, photons, gravitons, anything traveling at the speed of light, distances do not register in the same way. A photon does not experience time. It does not experience distance. It travels along what are called null geodesics, paths through spacetime for which the spacetime interval is zero. For a photon, the entire journey from the Big Bang to the present moment is, in a precise mathematical sense, instantaneous. This property, the conformal invariance of massless particles, is what Penrose exploits. In a universe containing only radiation, only massless particles, the concept of scale becomes physically meaningless. There is no massive particle to carry a clock. There is no atom to define a length. The universe becomes conformally equivalent to a universe of any other scale, including, Penrose argues, a universe that looks geometrically identical to a Big Bang. In other words, the far future of a universe containing only radiation is conformally indistinguishable from the very beginning of a new universe. The cold, expanded, infinitely dilute sea of photons that constitutes the ultimate fate of our universe has a geometry, when stripped of its scale, when viewed through the lens of conformal mathematics, that matches the geometry of a cosmological singularity, of a Big Bang. And if that is true, then the end of one cosmic aeon and the beginning of the next are not separate events. They are the same event, seen from different sides of a mathematical boundary. The death of our universe is the birth of the next. Now sit with the full implication of this. If conformal cyclic cosmology is correct, our universe is not the first. Before our Big Bang, before the inflationary epoch, before the plasma, before the recombination that freed the oldest light we can see, there was another universe, an older aeon with its own galaxies, its own stars, its own black holes, its own unimaginable history spanning timescales that dwarf ours in the same way ours dwarfs a single heartbeat. That universe expanded, its stars burned out, its black holes evaporated, its matter dissolved into radiation, and then, at the conformally equivalent boundary, where its end became indistinguishable from a beginning, our universe was born. But here is the part that transforms this from a beautiful mathematical abstraction into a testable physical hypothesis. The evaporation of black holes in the previous aeon was not perfectly smooth. Hawking radiation is thermal radiation. It carries information, it carries energy, and the final burst of evaporation from each black hole in the previous universe would have produced a pulse of gravitational radiation, a burst of energy in the gravitational wave spectrum, released at a specific moment in that aeon's history, propagating outward in all directions. Those gravitational signals would have crossed the conformal boundary. They would have survived the transition between aeons, and they would have left an imprint, a specific geometric imprint, on the cosmic microwave background of our universe. Penrose calls these imprints Hawking points. He predicts that they should appear as faint, circular rings of slightly anomalous temperature in the CMB sky, the gravitational echoes of black holes that evaporated in a universe that no longer exists. And in 2010, Penrose and his collaborator Vahe Ghourzadyan published a paper claiming to have found exactly those rings in the WMAP data. In 2018, working with Daniel An and Krzysztof Meissner, Penrose published a further analysis of Planck mission data, identifying what they described as anomalous points of high temperature in the CMB, candidate Hawking points, locations on the sky where the signal is statistically inconsistent with the standard inflationary predictions. The response from the cosmological community was divided. Several independent groups analyzed the same data and concluded that the signals were consistent with statistical noise, that if you look hard enough at random fluctuations, you will find patterns, and the patterns Penrose identified did not exceed the threshold required to claim genuine detection. Other groups found the analysis more compelling. The debate has not been resolved. The data remains. There is something important to acknowledge here, and it should be acknowledged directly rather than softened. Science does not arrive at truth by announcement. It arrives by the slow, contested, frequently uncomfortable process of hypotheses being tested, challenged, refined, and occasionally overturned. Penrose's framework may be correct. It may be wrong. It may be partially correct in ways that will take decades to disentangle. What cannot be said is that it is unscientific or that it is not being taken seriously by people with the mathematical credentials to evaluate it properly. What can be said is that the anomalies in the cosmic microwave background, the cold spot, the hemispherical asymmetry, the anomalous temperature points that Penrose identifies as Hawking point candidates, are real features of the data. They appear in independent analyses using independent instruments. They have not been explained by the standard inflationary model, and they are precisely the kind of signatures that a pre-Big Bang cosmology would need to produce if it were to leave any detectable mark on our observable universe. The light, in other words, contains patterns that our best model of the universe's origin cannot account for, and one of the most mathematically rigorous physicists in the world has proposed an explanation for those patterns that requires the existence of something before the Big Bang. Whether he is right or wrong, the question has teeth now. It has mathematics, it has data, it has a physicist with a Nobel Prize standing behind it, and a geometric argument that has not yet been refuted. The question of what came before is no longer purely philosophical. It is observational. But conformal cyclic cosmology is not the only framework that reaches into the pre-Big Bang era, and the others arrive from a very different direction, not from the future of a dying universe, but from the quantum mechanical properties of space itself. In the late 1970s and early 1980s, James Hartley at the University of California, Santa Barbara, and Stephen Hawking at Cambridge proposed what became known as the no-boundary proposal. Using the mathematical framework of quantum cosmology, a field that attempts to apply the principles of quantum mechanics to the universe as a whole, they proposed that the Big Bang singularity might not be a genuine boundary of space-time at all, but rather a point where time smoothly transforms into a spatial dimension. In ordinary space-time, time and space are distinct. Time has a direction. Events have a before and after. But in the Hartley-Hawking model, very close to the Big Bang, at the extreme densities and temperatures where quantum gravity becomes relevant, time loses its temporal character and becomes, mathematically, another dimension of space. The universe in this picture has no edge in time. It has no beginning, in the way we ordinarily use that word. It is finite, but without boundary, in the same way that the surface of the Earth is finite, but has no edge. Ask what came before the Big Bang in this model, and you receive the same answer that was always given, but for a different and deeper reason. Not because time did not exist before the Big Bang, but because the concept of before becomes geometrically undefined in the regime where time and space blend into each other. The question is not unanswerable. It is malformed. It is like asking what is south of the South Pole, not a question that reality has failed to answer, but a question that reality has shown to be asking for something that does not exist. And yet, even the no-boundary proposal, for all its mathematical elegance, does not close the question. Because the quantum state of the universe, the wave function that the Hartley-Hawking framework describes, is not uniquely determined. Different quantum states correspond to different universes, different histories, different physical laws. The no-boundary condition selects a class of possible universes, but it does not select ours specifically, and the question of why our universe has the particular quantum state it has, why it has the constants it has, the symmetries it has, the matter content it has, remains open. Beneath every answer, another question. Here is where the accumulated weight of these frameworks, inflationary cosmology, eternal inflation, conformal cyclic cosmology, the no-boundary proposal, begins to press against something that goes beyond physics, something that the mathematics keeps gesturing toward, but cannot itself contain. Every model of the pre-Big Bang era, without exception, must eventually confront the question of why any universe exists at all, not why our universe has the properties it has. That question, difficult as it is, belongs to physics. But why there is something rather than nothing, why the equations that describe space-time have solutions at all, why the mathematical structures that physicists use to model reality correspond to anything real. This is not a question physics can answer. It is not even clear that it is a question that has an answer in any domain of inquiry we currently possess. But it is a question that the light makes unavoidable. Because the light exists, because you are receiving it, because the universe that produced it, and the physics that governed its production, and the mathematics that describes that physics all exist, and their existence is not explained by any of the frameworks we have discussed. The light has traveled 13.8 billion years to arrive here. It has crossed a universe of extraordinary complexity and improbable structure. It carries within it the imprint of conditions that precede our Big Bang, possibly the signatures of black holes that evaporated in a previous aeon, possibly the fingerprints of a quantum state that selected our particular universe from a landscape of infinite possibilities. And at every level of depth to which cosmology has descended, from the plasma of the early universe to the inflationary epoch to the pre-Big Bang geometry that Penrose describes, the same structure repeats. Every answer opens into a larger room. Every explanation requires an explanation. Every beginning contains within it the seed of a prior beginning. The universe does not appear to have a floor, but there is something even stranger lurking beneath the geometry of Penrose's cycles and the quantum cosmology of Hartley and Hawking, something that does not arrive from the mathematics of space-time, but from the mathematics of information, from the question of what happens to the knowledge encoded in the physical world when the physical world ends. Because if Hawking radiation carries information, if the evaporation of a black hole does not destroy the information encoded in the matter that fell into it, but encodes it in subtle correlations within the radiation, then the previous aeon did not simply end. It transmitted. It passed something forward. Not matter, not energy in the ordinary sense, but information. A message written in the geometry of gravitational waves, carried across the conformal boundary, imprinted on the birth of a new universe. The oldest light in our universe may contain, woven into its coldest anomalies, a signal that was deliberately, if that word can be used without implying intention, preserved across the death of a previous cosmos. The universe may be, in some precise mathematical sense, writing to itself across aeons. And we, with our satellites and our detectors and our Nobel Prizes and our equations, are only now beginning to learn how to read the correspondence. What the next chapter of that correspondence contains is not a question about the past. It is a question about the deepest nature of time, information, and physical law. It is a question that has arrived not from philosophy, but from the most rigorous science we have ever practiced. And it is a question that, before it can be answered, must first be heard as the radical thing it is. The light is not simply old. It is not simply ancient radiation from a hot plasma that cleared and released it into the cosmos. It may be a letter from another universe, and we have only just begun to understand the language it is written in. There is a moment in the history of every scientific discipline when the tools it has relied upon reveal themselves to be insufficient. Not wrong. The tools of astronomy, the accumulated centuries of optical and radio and X-ray observation, have produced a portrait of the universe of extraordinary detail and fidelity, but insufficient, limited in the same way that a map, drawn only from what can be seen from a single hilltop, is limited, accurate within its domain, genuinely useful, but blind to the valleys it cannot see over and the territories that lie beyond its horizon. We have been following light. For the entirety of this journey, across 4 chapters and 4 layers of deepening mystery, light has been our guide and our subject simultaneously. The oldest light in the universe has led us from the epoch of recombination through the inflationary era, through the accelerating expansion and the closing of our cosmic horizon, through the pre-Big Bang geometry of Penrose's cyclic cosmology, and the quantum borderlands where time loses its direction. We have followed it as far as light can take us, and now we have arrived at the place where light stops. Not because the universe ends there, not because the physics breaks down, or because our instruments fail, or because the mathematics runs out of room, but because there is a wall that light cannot cross, a boundary that photons have never been able to penetrate, a region of cosmic history that electromagnetic radiation is constitutionally incapable of reaching us from. And in 2023, for the first time in the history of science, we detected a signal that came from the other side of that wall. To understand the significance of what was detected, you need to understand the wall itself. You already know part of this story from what came before. The epoch of recombination, the plasma that imprisoned photons for the first 380,000 years of cosmic history. Before recombination, the universe was opaque. Light could not travel freely. The cosmic microwave background is the oldest electromagnetic signal we can receive precisely because it originated at the moment the plasma cleared and photons were finally liberated. Everything before that moment, the inflationary epoch, the quark-gluon plasma, the electroweak phase transitions, the first fractions of a second of the universe's existence, is hidden behind a wall of opacity that no photon has ever crossed. No matter how powerful our telescopes become, no matter how sensitive our instruments, no matter how refined our techniques, we will never receive electromagnetic radiation from before the epoch of recombination. The physics of the early universe simply does not permit it. This is not a technological limitation. It is a fundamental feature of how light interacts with matter. The early universe was too hot, too dense, too electrically charged for photons to move through it in any way that preserved information about where they came from or what processes produced them. Any electromagnetic signal from that era was absorbed, re-emitted, scattered, and scrambled beyond any possibility of recovery. The wall is real. It has a precise location in cosmic time, and for the entirety of modern cosmology, it has represented the absolute horizon of observational astronomy. Beyond it, we were blind. We could model the early universe. We could infer its properties from the imprints it left on the CMB and on the large-scale structure we observe today. But we could not see it until now. Because gravitational waves are not light, and the wall that stops light does not stop them. Gravitational waves are distortions in the fabric of space-time itself. They are not electromagnetic radiation. They do not interact with charged particles in the way that photons do. They do not scatter off electrons or protons. They do not get absorbed by plasma. They pass through matter, all matter, every form of matter, including the dense, violent, impenetrable plasma of the early universe, with essentially no interaction whatsoever. A gravitational wave produced during the inflationary epoch, traveling through the plasma, through recombination, through the dark ages before the first stars formed, through the entire subsequent history of the universe, would arrive at our instruments today, carrying the imprint of the conditions that produced it, pristine, unscattered, unabsorbed, a direct signal from before the wall. Einstein predicted gravitational waves in 1916 as a consequence of general relativity. For nearly a century, they remained theoretical, their existence inferred from indirect evidence, most famously from the orbital decay of the Hulse-Taylor binary pulsar, which won its discoverers the Nobel Prize in 1993. Then, in September 2015, the LIGO detectors in Louisiana and Washington state detected the direct gravitational wave signal from two merging black holes for the first time, a chirp lasting less than a second, carrying the sound of two objects, each more massive than the Sun colliding at a significant fraction of the speed of light more than 1 billion light-years away. The detection was a triumph. It opened a new window on the universe. But it was a window looking at specific violent events, mergers, collisions, catastrophic processes, producing brief, intense gravitational wave signals against the otherwise quiet fabric of spacetime. What was announced in 2023 was something categorically different, something that had been suspected for decades but never confirmed, something that transforms gravitational wave astronomy from the study of individual cosmic events into the study of the universe as a whole. In June of 2023, 4 independent pulsar timing array collaborations, the North American Nanohertz Observatory for Gravitational Waves, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array, published simultaneous results in a coordinated announcement that represented more than 15 years of accumulated data. They had detected a gravitational wave background, not a single event, not a chirp or a burst or an isolated signal from one identifiable source. A background, a constant, omnipresent, low-frequency hum of gravitational waves permeating the entire observable universe, arriving from all directions simultaneously, a sea of spacetime distortions, so diffuse and so uniform that it must have originated from an enormous population of sources distributed across cosmic history. To detect this background, the collaborations used pulsars, rapidly rotating neutron stars that emit beams of radio waves with a regularity so precise that they function as natural cosmic clocks, accurate to within a microsecond over years of observation. A gravitational wave passing between Earth and a pulsar will slightly alter the arrival time of the pulsar's radio pulses, stretching space-time in one moment, compressing it in the next, producing a characteristic pattern of timing variations. By monitoring dozens of pulsars distributed across the galaxy simultaneously and looking for correlated timing variations that follow a specific mathematical pattern known as the Helling-Downs curve, the pulsar timing arrays can detect gravitational waves at frequencies far too low for ground-based detectors like LIGO to sense. The frequencies they are sensitive to correspond to gravitational wave periods of years to decades, and the background they detected, the hum that became visible in the correlated timing residuals of pulsars spread across thousands of light-years, is real. It carries the Helling-Downs correlation signature. It is not instrumental noise. It is not a statistical artifact. It is gravitational radiation, and it is everywhere. The most widely discussed explanation for the observed background involves supermassive black hole binaries, pairs of black holes, each billions of times the mass of the Sun, orbiting each other at the centers of merging galaxies across the history of the universe. As these pairs spiral inward over millions of years, they radiate gravitational waves continuously. Millions of such pairs, distributed across billions of years of cosmic history, each contributing their own gravitational radiation to the background, could produce the signal the pulsar timing arrays detected. This explanation is plausible. It is consistent with what we know about galaxy formation and the mergers that drive it. It is the conservative interpretation, the one that requires the least departure from established physics. But it is not the only interpretation, and the other interpretations are where the detection becomes genuinely extraordinary in its implications for everything we have been discussing. Because the gravitational wave background may not be entirely, or even primarily, astrophysical in origin, it may contain, woven into its spectrum, signals from the early universe itself. from processes occurring in the first seconds, the first fractions of a second, the first unimaginably brief moments of cosmic history, long before the wall of recombination, long before any star had ever formed, long before any black hole had formed through stellar collapse. Phase transitions in the early universe, moments when the unified forces of nature separated into distinct interactions, when the Higgs field settled into its current configuration, when the symmetries of the early plasma broke into the asymmetric world of distinct particles and forces we inhabit today, would have produced gravitational wave signals. The dynamics of the inflaton field during and after the inflationary epoch would have produced gravitational waves. If cosmic strings exist, one-dimensional defects in the fabric of spacetime predicted by certain theories of the early universe, their oscillations and intersections would produce gravitational waves with a characteristic spectrum. All of these signals, if they were produced, are still traveling through the universe today. They have been traveling since the moments that produced them, unimpeded by the plasma, unaffected by recombination, unabsorbed by any intervening matter. They are, in a precise sense, older than the oldest light we can detect. They are messengers from before the wall, and they may be present in the gravitational wave background that the pulsar timing arrays have now confirmed exists. The full decomposition of the gravitational wave background, separating the astrophysical contributions of supermassive black hole binaries from the cosmological contributions of early universe processes, is not yet possible with current data. The signal-to-noise ratio is real, but not yet sufficient to distinguish between sources with certainty. This will take time, more pulsars, longer baselines of observation, and ultimately a new generation of instruments. The most consequential of those instruments is LISA, the Laser Interferometer Space Antenna, where LIGO uses laser beams bouncing between mirrors, separated by 4 kilometers, to detect gravitational waves. LISA will use laser beams bouncing between 3 spacecraft separated by 2.5 million kilometers, arranged in an equilateral triangle orbiting the Sun. This arrangement gives LISA access to gravitational wave frequencies far lower than any ground-based detector, the frequencies at which the cosmological signals from the early universe are expected to arrive. LISA has been approved by the European Space Agency. Its launch is currently planned for the mid-2030s. When it begins operations, it will be, in a literal and precise sense, the first instrument capable of observing the universe before the epoch of recombination, not by detecting light, by detecting the distortions in space-time that the early universe left in its wake. We are building a machine to hear the universe before it became visible. Think carefully about what that means. The entire history of astronomy, from the first human eyes turned toward the night sky, to the Hubble Space Telescope, to the Planck satellite, has been the history of collecting and interpreting electromagnetic radiation, photons, light in its various forms, everything we know about the universe, beyond what we can reach with physical instruments, has been extracted from the behavior of photons that chose to travel in our direction. LISA will change that. When it is operational, we will have 2 independent windows on the cosmos, one electromagnetic, limited to the era after recombination, and one gravitational, extending in principle to the earliest moments of the universe's existence. We will be able to compare what the 2 windows show and identify by the differences between them, the physics of the era that light cannot reach. The universe has been speaking in 2 languages simultaneously since the moment of its birth. We have spent our entire history as a civilization learning only one of them. But there is a deeper implication here that extends beyond the technical achievement of gravitational wave detection. It concerns the nature of the information the gravitational wave background carries, and what that information does to our understanding of time, causality, and the boundary between the observable and the unobservable. We established in Chapter 3 that we live in a cosmologically privileged window, that the evidence of our cosmic origin, the cosmic microwave background, the large-scale structure of the universe, the expansion rate that dark energy is accelerating, is visible to us now, but will not be visible to civilizations in the far future, whose sky will be empty of everything except their immediate gravitational neighborhood. The gravitational wave background is a different kind of window, one with different properties, one that, in some respects, may be more durable than the electromagnetic window, even as the electromagnetic evidence fades. Gravitational waves do not redshift out of detectability in the same way that photons do. As the universe expands, gravitational waves are also redshifted. Their frequencies decrease, their wavelengths stretch. But the nature of gravitational wave detectors is such that lower frequency signals for certain detector configurations may remain accessible even as higher frequency signals fade. The cosmological gravitational wave background, stretched to lower and lower frequencies by the expansion of the universe, does not simply disappear. It shifts, and future detectors sensitive to those lower frequencies could, in principle, continue to receive it. The gravitational wave background is, in other words, potentially a more persistent record of cosmic history than the light. It is older, produced before the light horizon in many theoretical models. It is less vulnerable to the opacity that defines the light wall, and it carries information about processes that the electromagnetic record has never and will never contain. If the ancient light is a letter from the early universe, the gravitational wave background is an older letter written in a more durable ink from an era the light cannot remember. There is one more aspect of the 2023 detection that deserves careful attention, and it concerns not the origin of the gravitational wave background, but its implications for the inflationary models we discussed in Chapter 2. One of the most important predictions of cosmic inflation is the existence of a primordial gravitational wave background. Gravitational waves produced by quantum fluctuations in the geometry of spacetime during the inflationary epoch, stretched to cosmological scales by the rapid expansion and imprinted on both the cosmic microwave background and the gravitational wave spectrum. This primordial background is distinct from the astrophysical background of merging black holes. It has a different spectral shape, a different relationship between the amplitude of the waves and their frequency. Detecting the primordial gravitational wave background, separating it from the astrophysical background and measuring its spectrum, would be the most direct confirmation of inflation ever achieved. It would transform inflation from a highly successful framework for explaining the properties of the early universe into a directly observed physical phenomenon. And critically, the shape of the primordial spectrum carries information about the specific model of inflation that operated, about the shape of the inflaton field's potential energy, about the energy scale at which inflation occurred, about whether inflation was a single brief episode or something more complex. Different inflationary models predict different spectral shapes. LISA will be sensitive to some of those shapes. Future gravitational wave observatories, ground-based successors to LIGO, space-based successors to LISA, and the pulsar timing arrays as they accumulate more data, will probe others. Within the next few decades, we may not only confirm that inflation occurred, we may identify, from the gravitational wave record, precisely which model of inflation operated, precisely which version of the earliest chapter of the universe's history is the correct one. We may be able to read the inflaton field from the ripples it left in spacetime. And here is where everything converges. Here is where the journey that began with a simple observation about the uniformity of ancient light arrives at something genuinely staggering in its scope. The light told us the universe was uniform. Uniformity demanded inflation. Inflation implied a multiverse. The multiverse could not be directly observed, but the inflationary epoch itself left imprints on the gravitational wave background. The gravitational wave background, once detected, opens a window on the pre-recombination universe. That window reveals processes, phase transitions, symmetry breaking, the dynamics of the inflaton field that connect our observable universe to the broader landscape of physical law from which it emerged. And if Penrose's conformal cyclic cosmology is correct, if the Hawking point signatures in the CMB are real, if the previous aeon left its gravitational imprint on our cosmic dawn, then the gravitational wave background may contain not only information about our own inflationary epoch, but echoes of the black hole evaporations of a previous universe, a signal that crossed the conformal boundary, a message transmitted through the death and rebirth of a cosmos. The gravitational wave background is, in the most expansive interpretation of the current evidence, a palimpsest, a document written over and over by successive eras of cosmic history, each new layer partially obscuring, but not entirely erasing, the one beneath. We have begun to read it. We have the first confirmed detection of its existence. We have the theoretical framework to understand what it might contain. We have the instruments, in various stages of construction and planning, that will allow us to read it with the precision required to separate one layer from another. What we have not yet done, what no civilization in the history of the universe has ever done, is read the oldest layer, the signal from before the wall, the gravitational record of the universe's first moments. That reading is coming, perhaps within a generation, perhaps sooner. And when it arrives, when Lysa or its successors isolate the primordial gravitational wave background and extract from it the spectrum of the inflationary epoch, it will answer questions that the light could never answer. It will tell us which model of inflation is correct. It will tell us the energy scale of the universe's birth. It may tell us whether our universe is one of many or one of one. It will tell us, for the first time with direct observational evidence, what happened in the first fraction of a second of existence. But it may also tell us something it was not designed to tell us, something that no model currently predicts with certainty, but that the mathematics of several frameworks allows, something that sits at the intersection of gravitational wave astronomy, quantum cosmology, and the cyclic geometry of Penrose's aeons. It may tell us that something was happening before the first fraction of a second, that the signal contains frequencies and amplitudes that do not fit the standard inflationary spectrum, that there are features in the gravitational wave background that point unmistakably to a physics that precedes our own universe's birth. If that is what the data shows, and we do not yet know whether it will, then the discovery will not merely confirm inflation or distinguish between inflationary models. It will confirm that our universe has a history it did not begin, that the oldest signal we can detect is not the first signal that was ever sent, and that somewhere in the mathematics of space-time, written in frequencies we are only now learning to hear, is the story of everything that came before the beginning we thought was the beginning. The light has taken us as far as light can go. What waits beyond it is not darkness. It is a different kind of signal entirely, one that has been traveling toward us since before our universe existed, patiently crossing every boundary that separates the observable from the unobservable, waiting for the moment when something inside the universe it helped create became sophisticated enough to receive it. We are almost there, and what we will find, when the signal finally resolves into something we can read, will not merely change cosmology, it will change the question itself. There is a particular kind of silence that follows a genuine discovery, not the silence of an empty room, not the silence of absence, but the silence of something so large that the mind requires time to find the edges of it. Scientists who have experienced it describe it in strikingly similar terms across disciplines and centuries, a moment of stillness in which the world they thought they understood has not disappeared, but has become, without warning, much larger than it was a moment before. The instruments are still running, the data is still arriving, but the framework that was supposed to contain it has quietly, irreversibly split open at the seams. That is where cosmology stands today, not at the end of a solved problem, not at the summit of a completed ascent, looking back with satisfaction at the distance covered, but at the edge of a precipice whose depth has not yet been measured, holding instruments of extraordinary precision, reading signals of extraordinary antiquity, and arriving, with increasing frequency, with increasing certainty, at the conclusion that the universe is not merely larger than we imagined. It is stranger, stranger in ways that are not decorative, not philosophical ornamentation around an otherwise well-understood physical picture, strange in ways that penetrate to the foundations, strange in ways that the most rigorous mathematics available to us keeps confirming, chapter after chapter, signal after signal, anomaly after anomaly, in the oldest light we can detect. We have followed that light for 5 chapters. We have traced it from its release at the epoch of recombination, through the inflationary epoch that explains its uniformity, through the accelerating expansion that is gradually erasing the evidence of our cosmic origin, through the pre-Big Bang geometry of Penrose's cyclic aeons, through the gravitational wave background that opens a window on the universe before the light horizon. We have followed the physics as far as the physics currently goes, and now we arrive at the place where the physics stops, not because the universe stops, but because we do, because the instruments run out, because the mathematics, for all its power, arrives at questions it cannot answer from the inside. This is where the final chapter of this journey must be honest about something that most popular accounts of cosmology quietly avoid, not dishonestly, by omission, by the conventions of a genre that prefers resolution to open wounds. The honest thing, the thing that the data actually demands, is this: we do not know what the universe is. Let us be precise about what that means, because it is easy to hear it as a counsel of despair, and it is anything but. It is, in fact, the most exciting sentence in science. We do not know what the universe is, not because we have failed to look, but because every time we look more carefully, we find more universe than we had accounted for. The history of cosmology is not a story of gradual convergence toward a final answer. It is a story of perpetual expansion, not just of the cosmos itself, but of the domain of the unknown that surrounds our knowledge. Consider what we actually know. We know that the observable universe spans approximately 93 billion light years. We know it contains at minimum 2 trillion galaxies, each hosting hundreds of billions of stars. Each star, a nuclear furnace, producing the elements from which planets and organisms and minds are made. We know it is 13.8 billion years old. We know it emerged from a hot, dense state, and that before that state there was an inflationary epoch driven by a scalar field whose ultimate nature remains undetermined. We know the expansion is accelerating, driven by dark energy that constitutes 68% of the universe's total energy content, and that we cannot directly detect or satisfactorily explain. We know that a further 27% of the universe's mass energy is dark matter, invisible, inferred entirely from its gravitational effects, undetected by any direct measurement despite decades of experiments designed specifically to find it. That leaves approximately 5% of the universe that is made of the stuff we can actually see and touch and measure: stars, planets, gas, dust, everything you have ever encountered in your entire life, every object that has ever registered on any instrument ever built. All of it constitutes 5% of what exists. The other 95% is a mystery so complete that we have named it with words that contain the admission of ignorance inside them: dark matter, dark energy, dark not as a description of color or absorption of light, but as the oldest metaphor in human experience for what we cannot see, cannot understand, cannot reach. 95% of the universe is dark to us, and we are trying to understand the oldest light in the 5% we can see. This would be humbling enough on its own, but the anomalies make it worse, or better, depending on how you relate to the feeling of the ground shifting beneath you. In 2019, tension in cosmology that had been building quietly for years crossed a threshold that forced the community to acknowledge it openly. The tension concerns the Hubble constant, the number that describes the current rate of expansion of the universe. Two fundamentally different methods of measuring it, using fundamentally different physical processes and fundamentally different instruments, were arriving at different answers. Not slightly different, different by approximately 9%, different by a margin that, in a well-understood physical system, should not be possible. The first method uses the cosmic microwave background, the oldest light, to infer the expansion rate from the properties of the early universe, working forward through the known physics of cosmic evolution to predict what the expansion rate should be today. This method, anchored in the Planck mission data, gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The second method uses the cosmic distance ladder, a chain of calibrated distance measurements using Cepheid variable stars and type Ia supernovae, the same standard candles that revealed dark energy in 1998, to measure the expansion rate directly from observations of the local universe. This method, refined over decades by the team, led by Adam Rees using the Hubble Space Telescope, and confirmed by subsequent measurements, including those from the James Webb Space Telescope, gives a Hubble constant of approximately 73 kilometers per second per megaparsec. Both measurements are precise. Both have been independently verified. Both use well-understood physical principles, and they disagree. This disagreement is called the Hubble tension, and it is, at the time of writing, one of the most significant unresolved problems in physics. If neither measurement is wrong, and the evidence increasingly suggests that both are correct within their own systematic uncertainties, then something is missing from the standard. cosmological model, something that creates a difference between the universe, as the early light describes it, and the universe as the local measurements reveal it, something that changed the expansion rate between the early universe and today in a way the standard model does not account for. This missing something has a name in the community: new physics, a placeholder, like dark energy, for a gap in the framework, a signal that the model is incomplete in a way that the current data cannot yet specify. The oldest light is telling us one value. The local universe is telling us another. The universe is internally inconsistent in a way that our best theories cannot reconcile. And then there is the James Webb Space Telescope. Launched on Christmas Day 2021 and operational since mid-2022, the Webb telescope has been doing what it was designed to do, peering deeper into the early universe than any instrument before it, observing galaxies in the first few 100 million years after the Big Bang with a resolution and sensitivity that were previously impossible. What it has found has, with quiet persistence, complicated the standard picture of galaxy formation in ways that the community is still working to understand. The standard model of cosmology, known as lambda CDM, for cosmological constant plus cold dark matter, makes specific predictions about how galaxies form and evolve over cosmic time. In the very early universe, the model predicts galaxies should be small, irregular, and relatively low in mass. The large, well-structured spiral and elliptical galaxies we see in the modern universe should have assembled gradually over billions of years. Through the slow accumulation of matter under gravity and the progressive merging of smaller structures, what the James Webb Space Telescope has revealed instead is a population of galaxies in the early universe that are too large, too massive, too well-structured, and too numerous to be consistent with the standard model's predictions. Galaxies existing within the first 600 million years of the universe's history that contain stellar masses, the total mass of all their stars, comparable to the most massive galaxies in the modern universe. Galaxies that should not, according to the standard picture of structure formation, have had time to accumulate that much mass, to form that many stars, to organize themselves into such well-defined structures. One research team, publishing in Nature in early 2023, described their findings as galaxies that were, in their own words, impossibly massive, too big to have formed in the time available under the standard model. Candidate objects challenging the fundamental assumptions of lambda CDM cosmology. Not all of these objects have been confirmed as being as massive as initial photometric estimates suggested. Spectroscopic confirmation, the precise redshift measurements that definitively establish distance and therefore age, is ongoing. Some of the most extreme, early estimates have been revised downward as better data arrived. But the overall picture of a population of early galaxies that is more developed, more massive, and more structurally organized than the standard model predicts has not gone away. The oldest light is already challenging our understanding. Now the youngest light, the most recently observed, from the deepest reaches of observable time, is challenging something more fundamental: the model of how structure formed, the model of how the darkness of the early universe organized itself into the luminous architecture of galaxies and clusters and filaments. Two different signals, two different instruments, both pointing toward the same conclusion. The standard cosmological model is not the final word. There is a concept in the philosophy of science called a paradigm, introduced by Thomas Kuhn in his 1962 work, The Structure of Scientific Revolutions, one of the most cited academic texts of the 20th century. A paradigm is not merely a theory, it is an entire framework for doing science, a shared set of assumptions about what questions are worth asking, what counts as a valid answer, what anomalies can be safely set aside, and what anomalies demand immediate attention. Normal science, in Kuhn's formulation, is the work done within a paradigm, the filling in of details, the resolution of minor inconsistencies, the extension of the framework to new domains. It is enormously productive, and it constitutes the vast majority of all scientific work at any given moment. But paradigms have a life cycle. They accumulate anomalies. The anomalies are initially explained away, classified as measurement errors, attributed to unknown systematic effects, filed in the category of problems to be solved later. But if the anomalies persist, if they multiply, if they appear in independent data sets using independent methods, they eventually become impossible to ignore. And at some point, not always on a schedule anyone predicted, not always through the arguments of the scientists who identified the anomalies most clearly, the paradigm breaks. A new framework emerges that accommodates not only the existing successes of the old framework, but also the anomalies that broke it. This is not a failure of science. It is the mechanism by which science advances. The history of cosmology is itself a history of paradigm shifts, from a static eternal universe to an expanding one, from an expanding one decelerating under gravity to one accelerating under dark energy, from a simple Big Bang origin to an inflationary prehistory, from inflation as a unique event to inflation as a potentially eternal process producing a multiverse. Each of those shifts felt, from inside the previous paradigm, like an anomaly being taken too seriously. Each of them was, in retrospect, the recognition of something real. The Hubble tension is an anomaly. The oversized early galaxies are anomalies. The cold spot in the CMB is an anomaly. The hemispherical asymmetry is an anomaly. The power suppression at large angular scales is an anomaly. The gravitational wave background, with its as yet undecomposed mixture of astrophysical and potentially cosmological signals, is not yet an anomaly, but it is an open question of extraordinary depth. These anomalies may have ordinary explanations: systematics, miscalibrations, statistical fluctuations that look like patterns. This is always possible. It is always worth investigating. But it is also possible that they are telling us something, that they are the first indications of a framework, larger than lambda CDM, a cosmology that accommodates the early universe's oversized galaxies, and the Hubble tension and the CMB anomalies and the gravitational wave background within a single, more complete, more honest picture of what the universe actually is. We do not know which it is. Not yet. But here is what we do know, and it is perhaps the most important thing. This entire journey has been leading toward. The universe is not obliged to be comprehensible to us. This sounds like a concession, a surrender. It is neither. It is the single most productive recognition in the history of scientific inquiry. The recognition that the universe does not organize itself around human intuition, does not respect the boundaries of human cognitive architecture, does not limit its complexity to what a mind shaped by evolution on a small planet in an ordinary galaxy can immediately grasp. The universe is what it is. Its structure is determined by physical laws that operate without any reference to whether we find them beautiful or strange or disturbing or impossible to visualize. And what the history of cosmology repeatedly demonstrates is that the universe is more than we expected, always more. The expansion of the universe was not expected. Dark energy was not expected. Inflation was a theoretical necessity before it was observationally confirmed. The gravitational wave background was predicted, but detecting it required technology that took a century to develop after Einstein wrote down the equations. The anomalies in the CMB were not expected by the models that the CMB itself was designed to test. Every time we have built an instrument sensitive enough to hear something new, the universe has said something we did not anticipate. Every time we have extended our theoretical frameworks to cover new territory, we have found that the territory is larger than the framework. Every time we have approached what looked like a complete picture, we have discovered that the completeness was an artifact of the resolution, that a finer lens reveals more structure, more complexity, more depth. This is not a reason for despair. It is the universe's most consistent message about itself. It is, if you are willing to receive it fully, an invitation. The oldest light in the universe has been traveling for 13.8 billion years to arrive here. It crossed a universe of expanding spacetime, survived the clearing of the plasma, carried within it the imprints of the inflationary epoch, and possibly the echoes of a previous cosmic aeon. It arrived at our instruments and told us that the universe is flat, that it is uniform to one part in 100,000, that it began in conditions that demanded a history before the history we can directly observe. And then, in the anomalies, in the cold spot and the asymmetry and the power suppression, it told us something the models cannot yet explain, something that sits at the edge of the known, in the territory where paradigm shifts are born. We built instruments to read the light as precisely as possible. We found it beautiful and strange, and full of information about our origin. We also found it insufficient, not because the light is wrong, but because what it can tell us is bounded by a wall it cannot cross. A wall of opacity, a wall of expansion, a wall of causal disconnection that separates the observable universe from everything that lies beyond or behind it. And so, we turned to the gravitational waves. We built the pulsar timing arrays. We planned LISA. We began the long work of learning to hear the second language in which the universe has always been speaking, the language of space-time distortions, of metric perturbations, of the deep structural dynamics of the cosmos that electromagnetic radiation is constitutionally unable to convey. That work has only just begun. The 2023 detection of the gravitational wave background is not an answer. It is a confirmation that the question is real, that the signal exists, that the universe has something to say in this second language, and that our instruments are finally, after decades of effort, beginning to be able to receive it. What will we find when the resolution improves? When LISA opens its enormous baseline to the low-frequency gravitational wave sky? When the next generation of pulsar timing arrays adds more pulsars, more baseline, more sensitivity to the signal? We do not know. That is the honest answer. We have predictions, the primordial gravitational wave background from inflation, the phase transition signals of the early universe, the potential echoes of Penrose's conformal boundary. But predictions are not results. The universe has a long history of producing results that no prediction anticipated. What we can say is this: whatever we find, it will be older than the oldest light. It will carry information from before the wall. It will tell us something about the first moments of our universe's existence that no photon has ever been able to convey. And it may, in the most extraordinary scenario, that the current theoretical frameworks allow tell us something about what existed before our universe began. It may confirm that the Big Bang was a transition, not a beginning, that our universe inherited its initial conditions from a previous aeon, that the cosmos is not 13.8 billion years old but infinitely old, cycling through aeons of expansion and conformal rebirth, carrying information forward across boundaries that look like endings but are actually, geometrically, beginnings. Or it may tell us something else entirely, something no current framework anticipates, something that requires the next Guth, the next Penrose, the next Einstein to look at the data and say quietly, but without hesitation, that the model is not enough, that behind its successes lies a silence that sounds like an answer, but is actually a question nobody has yet been willing to ask out loud. You began this journey with a single, deceptively simple observation. There is light in the night sky that should not exist, light that is older than the universe as the standard model describes it, that carries within its uniformity the proof of a history before the history we can directly observe. You end it in a larger place, a place where the oldest light has led you to the walls of the observable universe, and through those walls to the gravitational record of the universe before visibility, and through that record to the question of what came before the beginning, and through that question to the recognition that the universe is not merely large and old and physically complex, but genuinely, persistently, irreducibly mysterious. Not mysterious in the sense of awaiting only a few more years of data before the mystery resolves. Mysterious in the structural sense, in the sense that every layer of resolution reveals more structure beneath it, that every answer contains within it the seed of a deeper question, that the universe appears to have no floor. The light that has been traveling since before the earth existed, since before the sun ignited, since before the first stars formed in the dark matter halos of the early cosmos. That light is still arriving, right now. At every point on Earth's surface, in every direction, the cosmic microwave background is present. Cold, faint, stretched to frequencies your senses cannot register, but real, continuous, the oldest sustained signal in the observable universe, arriving without interruption for 13.8 billion years, carrying its message from the moment the cosmos first became transparent. What that message says, what all of it, taken together, actually means, is something that no single framework has yet fully captured. It is something the physics is still reaching toward, something that will require instruments we are only now beginning to plan, mathematics we are only beginning to develop, conceptual frameworks we may not yet have the language to articulate. But it is there. The message is there. In the light, in the gravitational waves, in the anomalies the models cannot explain, in the tensions between different measurements of the same universe, in the oversized galaxies of the deep past and the accelerating expansion of the present, in the cold spot in the southern sky, that may be nothing and may be the echo of a universe that died before ours was born. It is all there. And the universe, whatever it is, however old, however large, however many aeons deep, however many layers of structure below the ones we have already found, is not finished speaking. We have not come to the end of the story. We have come to the end of what the light can tell us. And that is not the same thing at all.